He's an associate professor in computer science at the Heriot-Watt University in Edinburgh, and he is co-leading the Semantic Web Lab. His research focuses on practical data management and its application in information systems, utilizing and extending advances in knowledge management technologies to improve information systems. At the core, it's things like RDF, Sparkle, and the like. He works on challenges of integrating data from heterogeneous sources, where the heterogeneity can be from the way the data is modeled, represented, or the rate of change. And this is something where the technical people are really having fun while applying the semantic web technologies, because this is one of the key areas where those technologies can contribute. Alasdair, it's really a pleasure to have you here as of today, and the floor is yours.
Thank you very much. I guess I should maybe just add on to that, I'm also the chair of the Bioschemas Steering Council, and that is what I'm going to be focusing today on. So not so much on the live streaming of information, but more on the sort of findability. So how do we make data discoverable for everyone, and how do we make that in a lightweight, interoperable? So really going across science boundaries. So that's what today's talk is predominantly going to be focusing on. So, so making data discoverable, not just life sciences data. So I'm going to be focusing this very much though around the bioschemas and the approach that we've been adopting here. So this is a web page. This happens to be the web page for the Guide to Pharmacology, which is a data set about biomedical information. And we as humans, particularly the bioinformaticians, can interpret this page, we can read it, and we can see that there are some ligands and there's some proteins listed on this page. But to a computer, this is just gobbledygook. It can't make sense of this, particularly the search engines. When they interpret this page, they apply natural language processing. They can't really understand the meaning, what is intended here. So the schema.org approach is about embedding some lightweight markup within that. So just some JSON-LD, which in reality is just some RDF. And it's just some hints to the computer to tell it what this page has within it. So in here, we've got details that we've got a protein and a molecular entity, and some basic information about each of these. So the name, what disease it's associated with, because that's the important thing about this particular page is it was early on in the COVID-19 pandemic, and these were ligands and proteins that were identified to be important for COVID-19. So we're going to represent that markup just with the Bioschemas logo for now, and we're going to look at where this could be exploited. So as I've said already, one of the big key exploitations of this is the search engines. So they can interpret the intent and the meaning of the content of this page, not in the sort of domain detail, but in a lightweight way, so that they can really help people get to these resources about a particular gene or a particular protein. We can also use this within our scientific domains and going across domains as well. So we can put these into registries of data. And this way we can feed these registries through a single approach rather than having to have lots of domain-specific models and services from which we consume. And finally, we can use these into large knowledge graphs. So we can feed these and connect the information together and really extend science and our knowledge, but really getting back down to the links of where the data has come from and then drilling down into that so that we can get to the detailed models where they exist. So let's just look at how this works for search engine optimization. So schema.org came from the search engines as a search engine optimization technique. As I said, it's about them being able to interpret the meaning of a page. And we see this in the rich snippets that we get when we do a search. So here's a search for the film True Grit, or at least the keywords True Grit. And Google has interpreted that to be a film, which came out in 2010. And we see that we get some snippets here that give us it's a 4 out of 5 star on average. And we've got information about the production company, the budget associated with it. So that's in our search results. And then on the right-hand side, we get a knowledge graph representation of the information that Google know about this film, which it's harvested from various web pages, mostly containing this schema.org markup. So what is schema.org? So schema.org is a lightweight vocabulary of terms that allow us to talk about things that we find on the web. It was led by the search engines, so a group of 6 or 7 search engines, and is continuing to be developed today. So at the 14th release, which came out just last month, there were 792 things that we could talk about, the types, the classes, if you're in RDF. And then there are properties. So this is what we can say about those things. So these are the characteristics of the things that we're describing. And currently there's just under 1,500 properties. But the schema.org one is very much focused around e-commerce and the areas where web companies have had their major influence. If we try and do Google search into our scientific domains, so here's another example from Bioschemas. So we're looking for molecular interactions. And I've just entered in the two keywords, molecular interactions, but in my search, I was actually looking for data sets about molecular interactions. So this is an informative page. It tells me what a molecular interaction is, but doesn't satisfy my search needs because I wasn't able to express them clearly enough. So if we just carry on looking at this a bit further, this is trying to look for molecular interactions data. So I added on the fact I'm interested in data, but we're still not quite getting data back. We're getting articles about molecular interactions data back, which is a step closer because we could follow through the articles and get to the data. But what we really want to do is actually get to the data itself. So we can, this is from November 2021, and we start seeing results coming through from Google's dataset search. So that's what this top hit here has come through from. So what is Google's dataset search? Dataset search is a dedicated portal for searching for datasets, and it's populated with markup from the web conforming to the dataset profile. So here I do my search for molecular interaction, and I get as a top hit this molecular interaction database, MINT, which is a leading database in that area. We also get 3 other hits appearing on this sidebar here. There's a few more that appear if you scroll further down, but these are different levels. So this one at the bottom is another representation of MINT and a few other data sets coming through there. As I said, this is all based off this schema.org, this lightweight vocabulary of terms that allows us to describe a data set. And it's got a very loose definition of what it means by a data set. So a body of structured information describing some topic of interest. So this is kind of very much feeding into this area of the web where search can be very loosely defined. We're looking for things to get back. Okay, so we're looking to increase our recall there. The challenge with dataset is it's got over 120 properties. It's actually close to 150 now. And some of these are very easy to use, like name, description, but some of them don't really make sense for a dataset. So is a dataset family friendly? That's actually a property to do with films and books and other sorts of media. But because of the inheritance within schema.org of dataset coming from creative work, it gets these properties as well. And this makes it very challenging for people to reuse this vocabulary for their particular datasets. So Google have gone and said, right, okay, we'll provide some guidelines on the properties you should use. And we'll limit these to about 10, because that's a nice, reasonable number that someone will add in reasonably quickly to their page before getting sort of too overwhelmed by the number of properties. And at the top level, they only require 2 properties to be given. So the name of the dataset and a short description of it. Then they have recommended properties like citation, identifier, keywords, and license. So this gives a bit more information to allow you to understand what the search result is and discriminate between the results. Bioschemas is a community initiative started about 7 years ago now. And the idea is to take this search engine optimization approach and apply it to life sciences resources. So we want to improve the discoverability and interoperability of life sciences resources. And we do this in 3 key approaches. So the first is we extend the schema.org vocabulary of terms to be able to describe life science resources. And so far, we've had 6 of our proposals merged into schema.org. We also provide usage guidelines over the schema.org types and our extensions of them. And these are based around this 6 minimal property principle. So we really want to make it quick and easy for people to deploy markup. And the final pillar of Bioschemas is to provide software to support people in developing markup, consuming markup, validating the markup, and doing other things with markup. Okay. On the right here, we've got this the Bioschemas approach. So it's based on the schema.org model with extensions, which are represented in green here, and then layering documentation, marginality, so whether a property is minimum, recommended, optional, the cardinality, whether you're expecting one copy of a property or multiple, and what we're expecting as values back for these things. So the controlled vocabularies, the domain-specific controlled vocabularies that you could put in as the object values. Now, one of the things we were accused of quite early on when we started our development was there are many vocabularies out in the life sciences world. There are hundreds of these, almost thousands probably. And those ontologies have had a lot of development time spent on them, and they model the detail of bioinformatics very well, but they're not so good for the search area. So Bioschemas is really adding a layer on top of these as a lightweight set of semantics to support search and some lightweight exchange, probably going across domain boundaries to enable others to be able to find and reuse your data. So that links us into the FAIR data principles. So Bioschemas is very much focused on the findability aspect, but we also touch on the other areas. So it's retrievable data through a standard protocol in an interoperable representation using standardized vocabularies, and it's reusable because we provide license and you can add provenance into your data. So the Bioschemas community, it's developed 23 types to date. We've got 37 profiles, 61 deployments within Elixir, 83 sites with markup within them. We've got over 162 profile deployments over those 83 sites. And we reckon over 80 million pages, probably getting close on to 100 million pages now with Bioschemas specific markup within them. So markup, how do we go about deploying it? What does it look like? Okay, so here is a page. This happens to be the mass bank record, and we can embed markup within this. Okay, so we can use the molecular entity markup, and we can check that others can consume that markup by using a schema.org tool, the validator, that is able to, in real time, extract the content from that page and show us the machine readable representation of that. This conforms to our molecular entity profile. The profile doesn't fit very well onto a slide, but on the top, well, on the left here, you've got our 3 minimal properties for this profile, and an expected type and a description. And then you've got our recommended properties coming up on the right here. So there's a few more recommended properties for the molecular entity profile. And then over on the right-hand side are the marginality level, the cardinality levels and the controlled vocabularies and example usages of these. So this is all about helping developers to put markup within the pages. Adding markup to your resource is fairly straightforward. The first thing you need to do is decide for your resource, what is the appropriate type of markup that you want to do. Then you need to find a mapping between the elements on your page to the Bioschemas profile elements or types that we have. And to help you with this, we provided a markup generator, as this is a simple web form where you can fill in the properties from your web page, and this will then generate the JSON LD snippet that you can copy and paste into your website, or you can then use as a templating mechanism to embed into your website deployment mechanism so that you read the data out of your database and display that on your page. This slide's just to give you a feeling of where the Bioschemas more specific deployments are. We have a live page that lists all of the deployments that we know of. And as I say, there's over 100 of these deployments to date over across our released profiles. So deploying markup is all good and well, but if no one's using it, it doesn't make any difference. So how are we exploiting the markup? And this also helps drive the development of the markup profiles to help us better understand the markup that we should be putting into the sites. So one of the early deployments of Bioschemas markup was the Elixir TESS, which is the training and events registry within Elixir, which is the bioinformatics infrastructure. And what they did was they deployed Bioschemas markup conforming to the course instance and training material types within schema.org. So we developed profiles over those that allowed us to feed the test database with information that was relevant to the courses and the training events and the training materials that were made available across multiple sites. These were then harvested and are continuously harvested by the test crawler into the test registry. The great thing here is there's no need to understand custom APIs, different website layouts, developing custom scrapers for each site, because all of this is embedded within the HTML. So you just do a HTTP GET request, you get the content that way and extract the JSON LD from it. In this case, there's no need for concept merging because each site provides information only about their training events. So we don't get the same information from multiple sites. This then allows us to provide a dedicated portal over this. And in this case, I've got a search for toxicology, and this shows the training materials that are available for that. So rather than being a generic search for toxicology, which would give very different results, this one is very much dedicated to finding those training events, the training materials for that. Another way that Bioschemas is being used is to feed registries with information. So in this case, we've got the workflow hub. So workflows can be described, computational workflows can be described according to the computational workflow profile. And these are then fed into the workflow hub registry and allow it to generate pages about each individual workflow. Another area of focus is the intrinsically disordered protein. And what they want to do is apply the approach that TESS had, but for their own specialist resources. In this case, we've got 3 resources at the moment. There are many more within the IDP community, but we started with 3. And these 3 resources have overlapping content. But what we're looking at here is the protein sequence, and annotations on those sequences. And what we want to do is feed these into a central registry that would allow us to combine this information at a high-level aggregated way so that others can search across all known intrinsically disordered proteins to then drill down into the information about specific proteins that they're interested in. To do this, we developed a tool called Bimuse. So Bimuse is the Bioschemas markup scraper and extractor. And this is what we used for harvesting the data within the sites and feeding them into the registry. Again, there's no need to learn custom APIs, deploy custom web services on each of these sites. This is just simply HTML accessible through HTTP GET requests. However, in this case, we do need to do concept merging. These sites have overlapping content. So we need to identify when we have the same protein from these different sites so that we can, rather than have multiple records for the same protein, merge this information together. So the 3 sources that we had were Disprot, which is a site that is curated from publications and contains just over 2,000 proteins. MobiDB, which is experimental and predicted protein sequences that are known to be intrinsically disordered. And they have over 189 million protein entries, but they've only included 2,000 or so within their sitemap at this point. And then there's the Protein Ensemble, which is a deposition database that deals with structures of proteins. So this typically, or protein ensembles. So this is 2, 3, 4 proteins mixed together and experimented on, and then getting information out from that. So they have 172 protein ensembles representing about 90 distinct proteins. Each of these conform to the Bioschemas protein markup model or profile. So at the center of this, we have the protein with the minimum information of an ID and a name. And we also encourage the use of same as links so that we know which proteins are equivalent to each other in different data sets. Each protein has a sequence, and this allows us to know what the nucleotide protein sequence is within that. And on top of that, we have an annotation. And this is typically, in this case, how that protein is known to be intrinsically disordered. The protein is known to be associated with a specific species, as we have a taxonomic range. And this information's come from a specific data set and is the subject of a scholarly article. Now, these ones down at the bottom are there to allow us to connect this information into larger knowledge graphs. And I've noted OpenAir in this case. And then over here, we've got the property values. These are the annotations on the protein sequence, and these link into existing ontology terms. So we can reuse term codes from ontologies to really give specific information about the type of annotation that we're talking about. As I said, we used Bemuse to extract this information. So Bemuse was purpose-built for the Bioschemas community. It can deal with either a list of URLs that you give it or a sitemap. It extracts markup that is embedded as either JSON-LD or RDFA, or in some cases, sites just choose to put both of these in using different markups in different blocks of the site. One of the big challenges we had with the extraction was sites that have dynamic generation of the content, so single page applications using React frameworks and so forth. These put a lot of the processing cost onto the consumer of the information. So you need to be able to render the web page before you can extract the content from it. Bemuse also adds on a bit of provenance information because we wanted to know where we've got information from, when we did it, and which version of our tool did you use to get it. This is so that you can track back on the information, debug information when that happens, because websites are constantly changing. So that's why we need to know when we've got the information. And the idea is that we can then harvest this markup and create it into a knowledge graph. But to do this, we need to be able to merge the concepts together. We need to go from the page-centric view that is the web to a concept-centric view that is the knowledge graph. So to do this, we exploited information that was within the markup. So as I said, we encouraged the use of schema same as representations to tell us when you know that you have the same protein in different data sets. Because very often the data provider is in the best place to tell you that their record about a particular protein is the same as another record about a particular protein. However, it still isn't very straightforward because there are a lot of URLs representing the same protein, even within the same data resource. So a favored resource for proteins is UniProt, but UniProt have both the web representation, the web page representation, and the RDF entity representation of the same protein. And some sites link to the page and some sites link to the entity. So we needed to deal with these differentiations as well. So, and then once we've decided that we're going to link these information together, we need to give that final thing a URL, a distinct identity. So in this case, this was being done for the IDP Central. So we based our accession numbers off UniProt and gave them a new IRI base for that. The second thing we needed to choose was when we get information from different sites, we get the same information sometimes. So we get names from both sites. But in this case, you can see in red that these names are different. So in the first site, Disprot, they're given the Disprot identifier plus P27 KIP1 protein. Whereas in the MobiDB, this same concept is giving us the UniProt identifier and then a slightly different name here. But these two things have been said to be the same. If we look at the taxon, we see that we've got Homo sapiens and Homo sapiens human. So these are slightly different. To us as humans, we can interpret that, but machines stumble over these sort of differences. So we had three choices that we could do. The first was to pick a canonical source so that we would always choose the values from one source and then supplement it with entries from others. The other option is to concatenate all these entries together. And this is very useful for things like synonym, where we do want to bring all of these information together. Or the third approach is to keep track of everything and make sure you know where each piece of information has come from. I call this the Wikidata approach. So it's keeping statement level provenance. So we followed this Wikidata approach, and this was what we managed to achieve in our harvest of the IDP sites. So we wanted to verify that we were getting the correct information and that we were merging it together correctly. So what you see in the table on the left is that from the sources, we got certain information, and after our harvest, we got exactly the same information out. So this gave us confidence in the approach. And this Venn diagram on the right shows us the overlap of these different sources. So we can see that across the three sources, there are just 44 proteins that are known in all three sets. So there are 34 unique ones in PED itself. The other thing we wanted to do here was to provide some interfaces over this data. So the first thing we were doing was providing a Sparkle endpoint. And we provide this with the Snorkel Extended Edition interface. This allowed us to provide canned queries so that users can very quickly just go, right, I'm interested in finding the annotation count per protein. So you can click on that query on the right-hand side, and this gives us the results. So you don't have to write the query yourself. The other thing we were able to do with this approach is these queries were all stored in GitHub, and we used a service called Garlic to provide a REST API over the IDP knowledge graph. So here you can see various methods that are available. So we've got protein count, protein search, and these are all based on Sparkle queries behind the scenes. So this REST or this Garlic API just gives us a layer over the top of our Sparkle queries and allows you to return CSV or JSON from it. And what we're now building up on top of this is the IDP central registry. So we're still in the early days of this, but we're making some progress towards making this into a sort of fully fledged prototype system that people can really start searching and getting, for the first time, a view of the proteins across these three sources. Every year, Elixir run a biohackathon. So this last year, we were organizing a data harvesting hackathon topic. And what we wanted to do was demonstrate that this Bioschemas approach works, that we were able to harvest markup from multiple sites and bring it together and deploy it through a Sparkle endpoint. So we set ourselves the challenge of how much can we harvest in a month prior to the hackathon? And during the hackathon, what can we do with that information when we've got it? What we discovered was harvesting is slow and time intensive, particularly when you have dynamic pages, because you have to render each page and then extract the markup from it. So in time for the hackathon, we managed to partially harvest markup from 25 sites. And it was a very small percentage of these sites that we were able to harvest. This translated to about 11 million, 12 million triples and represented about 413,000 pages that we were able to harvest in that month. We wrote queries over this and we provide these through a Jupyter notebook, through a sort of GUI that we created within that. And we can see that we get some interesting results back here. And what I wanted to highlight is that the markup itself that we get from all of these different sites is very messy. So what you see here is our top one here is gene, but this is bioschemas.org gene, and there are 238,000 resources with that. At the bottom of this screenshot, you see schema.org gene, which is actually the correct URL for the resource or the class that we're talking about, but there are only 39 pages with that markup within it. So the challenges are around consuming the information, but also once you get that information, it's very messy. OpenAIR is an initiative to build a research knowledge graph across all of the world's research resources. And what they're interested in doing is connecting datasets to publications, to authors, to projects, and so forth. So at a very high level, so you can really try and get an understanding, an overview of the world of research. And what we're exploring here is whether the Bioschemas schema.org approach is a good, valid approach for feeding the information into this knowledge graph, going beyond what the existing large registries have. By using the schema.org approach, we have shown that there's no need for custom APIs, but we have shown that we need to merge concepts when they come from multiple sites, which would be the case here. In the case of OpenAIR, we also need to do a terminology transformation. So the OpenAIR research graph is based around the DataSite model, whereas the markup is based around the schema.org model. So we need to map from one to the other. And that needed an extension of the DataSite model to have these high-level representations of these biological concepts. but we hope to expand this across other scientific domains into the future. So the whole idea is once we've got that information within the open research graph, that we can then provide this into added value services on top of that. So we harvest the markup just using HTTP GET, we map it into the DataSite knowledge graph representation, and then have value added services over the top of that. So I'm just going to finish up now. First of all, I'm going to give you a reminder of what we talked about. So Bioschemas is about making life sciences resources more discoverable on the web by embedding machine markup within them at a lightweight vocabulary level, which can then be exploited across the whole web using standard HTTP GET requests. So this makes it available to the search engines, to our own life sciences specific registries, but also to domain agnostic knowledge graphs that can then exploit that markup. The approach we followed is looking at search engine optimization, which embeds some machine readable markup to give a high level interpretation of what the page is about. To do this, we've extended the schema.org vocabulary for the life sciences, but this could equally be done for other domains. And we've been working with the agri-science domain and the material sciences domain to look at how they can follow our approach and do their resources in a similar way. The other key element is to provide guidelines, the profiles, to tell you which properties are the most pertinent to use when you're marking up your resource, and to provide software and documentation to help people, or tutorials, I should say, rather than documentation, to allow people to understand how to deploy this markup, how to extract the markup, and how to process it afterwards. And as I've tried to highlight, there are some challenges here. Okay, so we're still not got answers to some of these questions. So we know that we can extract the markup using HTTP GET, but this, in doing it on a page-by-page basis, is a very time-intensive, resource-intensive approach. And this has been recognized by the search engines as well. So it's intensive both on the provider, who has to have lots of database calls, but also on the consumer, who has to materialize the information and then extract it. So the solution that's being discussed here is about making data dumps available as data feeds at well-known locations within a site, using the schema.org vocabulary of terms. The other element is that the data quality is very variable, with a lot of variability in the IRIs that are used to describe things and the conformance with our profiles. So I highlighted this with the different IRI bases, so the Bioschemas gene and the schema.org gene. And we're now starting to see the first versions of validators coming through. So we can use the schema.org validator itself to check that the markup is extractable and that it meets the syntactic requirements of JSON-LD or RDFA and uses terms that come from the schema.org vocabulary. Now, you may notice here that there are some terms in red. This is because Bioschemas extends the schema.org vocabulary, and when we use new classes, new properties, these are returned as errors by the schema.org validator. So to overcome this and to also apply our profiles, we're starting to develop our own validators, which will allow us to use our own prototype types and properties, but also to have some understanding of these conformance profiles so that we can check whether all of the minimal properties are there and are there with valid objects at the end, so that people can really consume this information. So I'd just like to acknowledge that this isn't all my own work. This is the work of the whole Bioschemas community. This set of names is incomplete. There are far more people who've been involved over the years than are listed on this slide, but we've just not been very good at keeping track of them. And this are where you can find some more information about Bioschemas. So obviously the website, but you can also find us on GitHub and on our Slack. And if you really want to find out more, you can join our monthly community calls on the fourth Monday of each month at 5 o'clock Central European time. So thank you.
Thank you, Alasdair. Thank you very much for this inspiring talk and for the very good overview of the activities and Elixir and the bioschemata. In some to a certain degree, it reminded me also to activities in the gene ontology. And I think one common denominator is that you have unique IDs for referencing proteins or genes on the other side. And then you try to link documents to those identifications. And I think it's a very relevant question also for communities such as chemistry, material sciences, where you have a similar case. But maybe there are even further NFDI people here from other communities that start thinking on how such an endeavor could help their own domain work. So it's really time for questions now, and I'm looking into the community. Please raise your hand or please use the chat if you want to ask a question. Yes, Stefan, please.
Hi, thank you very much. This was awesome, a fantastic ride through the entire story. So I really love that. I would like to challenge a bit of the title where you said it's about the findability. And what I found even cooler and even more important is the interoperability stuff, the portal that you have set on top of the IDP resources to actually make use of that. So I think findability is really just a very tiny piece of what you have there.
I guess it depends on where you see findability stopping and interoperability kicking in. Because as I've tried to highlight, we're doing this at a very high level. So you're not getting the full details of any specific concept. So you wouldn't get the full details of your mass spectrometer results coming out. To do that, you'd want to use the detailed domain vocabularies that are being developed in these specific domains. So that's why we focus more on the findability element, partly because it helps us keep our focus on this lightweight approach, rather than, as you maybe saw, the rabbit hole, where when we lose track of that, we end up getting down into the rabbit hole, going, right, let's try and connect this very specific bit of information with this other very specific bit of information. And you know, there are much better ways of doing that with very detailed domain ontologies. So yes, we can do cool interoperability things, data exchange at a high level. And particularly, I think this is where going across domains will be a very sort of good driving case for the level of detail that we would need. And I think that fits quite nicely with that findability story. So yeah, the two kind of go hand in hand, I feel.
Yeah, I subscribe to that point of view, actually, fully.
Yeah.
I take another question from the chat from Matthias Löber. I just repeated, or Matthias, do you want to ask the question by yourself?
Yeah, I was wondering how the relation is between Bioschemas or schema.org and the W3C DCAT vocabulary, which seems to be or address a very common goal.
Yeah, they're very, very similar. So Bioschemas uses the schema.org vocabulary at that point. So this is dataset and data catalog. And we've provided our own profile over that, but that is in line with Google's profile. When schema.org community were developing the dataset type, they were very inspired by the W3C DCAT, and you'll see that the dataset definition is very, very similar to the DCAT one. The data catalog idea is very similar to the DCAT one, and the data download is very similar to that as well. And they do actually acknowledge that on the schema.org website. So the reason why they don't use DCAT directly is they wanted to have a single vocabulary that encapsulated everything. But I believe there are mapping files that kind of essentially say these are OWL equivalent class, OWL equivalent property that have been published to sort of really acknowledge this very close relationship.
Okay, thank you.
Yeah, I remember nights of discussing the differences between OWL and RDF and OWL same as and different from and stuff like that. And it turns out it's really useful for that use case. Is that true?
The OWL same as, so if you notice, I actually use schema same as. So this is again, a lighter weight interpretation So it doesn't have the sort of same connotation of actually enforcing that the two resources have to be identical. But again, it's also about having everything encapsulated into a single vocabulary. But then this poses challenges to the schema.org community of how far should their vocabulary of terms expand out. And this is why they've been very sort of, they wanted to see very distinct use cases from us and actual uses of the bioschemas types before they would include those into the schema.org vocabulary. So it took us quite a few years to be able to sort of get to the point where we had deployments and we had the consumption stories to demonstrate that there was a use and that we had the correct properties that would enable these.
But I mean, if you resolved this in the community and you got the shared idea on how to do this, then the large part of the work is done, right? Because this seems to be like the major the cornerstone on which you can build the whole house.
So as long as you accept that in the Bioschemas schema.org world, you're in a very lightweight semantics and you will end up with messiness and you will end up with errors in that data, and you're happy to just accept someone's claim, then yes, you have a very good starting point. Another area of my work has been with BridgeDB and the Open Facts community. And there we were looking at allowing people to say, I believe your set of mappings of these same as equivalences versus these other ones. So it was about separating out these equivalence statements from the actual data and then being able to say, right, in this circumstance, I want to turn on your equivalences. Whereas in other cases, I want to turn them off because I don't trust them or I need to be a bit more precise. And that's when, and I guess this is where the SSSOM work comes in, which is another representation for identifying mappings and giving them context and differences in levels. But again, that's all very low level nitty gritty things, not this world of schema.org bioschemas, where we just say, right, there's some equivalence, but we don't worry too much about what that equivalence is.
Okay. Are there further questions from the community? Yes, Stefan again.
So on one of the slides, you basically implied that there's a one-to-one relationship between the things in the web page. And because you said this is the entity URL of it, and that is the web URL of it. And there's also cases where you have like relationships between things, and the interaction, or maybe call it chemical reaction or whatever, will require two molecular entities, a molecular entity and a protein and so on. So how is that linking between things being done? Is that part of the interaction class, for example?
So this actually comes straight from the RDF basis on which we're operating. So JSON-LD is just RDF at the end of the day. So I'm sorry if I've given the impression that there's a one-to-one representation between the content markup and a resource. You can obviously have multiple resources within a page. And in fact, just thinking of a quick slide I can jump to, this one has a case of that. So this has several ligands and multiple proteins all on the one page. And within the markup of that, you'll find that there is, there were different blocks. There you go, there's the markup. So we've got two blocks of markup here, and then these have different IDs on them. So these @IDs are the IRIs that identify the resource within the page. And then the other way you can use these @IDs is as targets. So I don't actually have an example on this slide. I can't think where there is one in the slide deck. But what you can do is you could say the associated disease, and then you would have a block of JSON-LD nested within that with an @ID, which is essentially a pointer to another IRI, and then maybe some basic details about that. So you can nest markup within either that page, or you can link over to other pages. one of the common practices within schema.org is when you link over to another site, you would still give the type and the name of what you're linking to, so that consumers don't necessarily have to follow that link to get that content or that very sort of immediate content. But if you wanted more detailed content, you would then follow that link.
All right. There's a question from Roman Baum. Roman, do you want to make the question by yourself? Otherwise, I just read it from the chat. Okay. No problem. I take it from the chat. So the question is, was there a point where you think about the use an IRI of identifier.org instead of an IRI of a specific resource? Or in other words, what will happen with deprecated IRIs? Good question.
So the use of IRIs is up to the individual data provider. So if they choose to use identifier.org IRIs, that is perfectly acceptable. But obviously, when you start consuming this information, you need to be able to knit together all of these different IRIs. So we don't have any magic solution to this. This is a sort of challenge that has been plaguing the semantic web community for quite a long time. And this is where the same as equivalences come to the fore. So yeah, we could very much use identifiers.org. And in fact, do I actually even use those on these? So you can supply multiple identifiers. So that's what this identifier property can be used for, but also the URL can be used to provide other alternative URLs known for that resource. So you could provide it in multiple ways. So you could give the resource of the ID of the page as your base IRI, but then use identifiers.org or other IRIs as equivalences there. And for those who don't know what identifiers.org is, it's a registry of known databases, and you can actually do something called compact URIs with them. So with identifiers.org, you could do identifiers.org/uniprot:p12345, and then that will resolve to whatever the current uniprot web page is for the protein P12345. So uniprot is a registered little string key namespace for the uniprot database.
So maybe I can add a question for myself. If you think now about materials, then of course the identification of materials becomes at the core of the activities, and then maybe the modeling with chemical formulas is not far away. Do you know how successful your approach can be transferred into these domains? Because you mentioned those domains by yourself.
Yeah, so we've been starting to work with the material science domain. I mean, obviously, the challenge of how you identify a particular concept is very much domain specific. So I've not been involved with them at that level, but I'm sure they have their own ways of doing this. With the chemicals, obviously, there are multiple ways of identifying a chemical, and we try and provide mechanisms for doing that. So if you look at the chemical profile, you'll see that there's the INCHI representation, the SMILES representation, and you can end up with multiple SMILES representation for the same chemical with an INCHI, I believe. So there is already that discrepancy at that level. But it's very much up to the data provider to decide what is the resource I'm going to describe, what type it has, and what are the key properties I'm going to provide for that. And then the consumer can choose whether they use that data or not, and then how they're going to use that. So I'm kind of deflecting your question a bit, but it's kind of at that level of choice. So we try and stay away from those nitty-gritty domain questions.
That's why we have the domains on board, right?
Yes.
And here's another question. Can you give more details about reasons that affect the quality which needs more validation? From Al-Zayed, Al-Jagabi.
So thanks for the question. Yes. So very often the people providing this markup are not semantic web specialists. So they don't understand that we had the example of the two UniProt IRIs, and to them, they're just the same thing. They both represent UniProt. But to us, we know that to a machine, these things are different. So a machine will interpret this Perl differently from this web page resource for that. So this is sort of the challenges that we have. The other things were developers would put the block of script JSON-LD after the closing HTML tag sometimes. And that just isn't accessible to any library because any HTML processing library reaches the closing HTML tag and it finishes. Other things that crop up quite commonly are you put in so a lot of people are generating this from databases where they maybe have descriptions which include quotation marks. And then you just extract that directly into the JSON-LD and you end up with these quotation marks which have specific meaning within JSON-LD and they haven't been escaped properly. So this is why we need the syntactic validators, and that's what the schema.org validator does. But then we want to be able to layer on these profiles over the top of that so that people can understand whether they are providing the minimal properties and the recommended properties, and that others will be able to consume and reuse that information in a meaningful way. So the validators are really there to provide some level of consistency in the markup across the different sites. So but I mean, validation is a very thorny and difficult issue. So these two validators, in fact, all these three are validating the same page. And even within this validation report here, we see that the result is not valid. But if your eyesight is good enough, you read the marginality report and it says all minimal properties are present, but it's got a red 1 here. So even within that, and this is because the data value is present, but it didn't have a conformant type for it. It was meant to be a date time, and it was not quite conforming with the XML date time model. But here they only had one issue, whereas this one, which is extracted on the same day, the same page, they were conforming to the same profile. They had 3 issues on that profile, and then multiple recommendations of how to improve it. So we're still trying to understand exactly how to validate a page. So we can provide the sort of machine representation of that now, but then how you interpret that and present that to the user is also an interesting research challenge at this point.
All right. I don't see any further questions. So this brings us to the end of this, also this streaming event. Thanks for joining live, or thanks for joining later if you watch this video afterwards. A great applause to our today's speaker. I think the work that you're doing is awesome. Please keep on doing that.
Thank you.
And I think there's plenty of room for collaboration also if you